We're on Arduino Workshop 6. And so yeah, like I said, we're going to talk about motors today. And then next week we're going to talk about the specifics on how brushless, servo, and stepper motors work. So today we're going to kind of treat the motor as a black box that basically we give it a current, it spins one direction, we swap our connections, it spins the other direction. But probably you guys know from like physics classes sort of how a motor works. Current flowing through the motor generates a moving magnetic field, and then you have a shaft that's attracted to that magnetic field, and so it turns. Obviously there's AC or DC motors. We're going to focus on DC motors because in robotics we primarily use batteries. Just in general, a lot of the, like when you're picking out a motor, you're going to want to check the characteristics of RPM, torque, voltage level, current consumption, and size. Like if you were going to buy a motor for your own little hobby project, these are probably the top 5 things to think about. And in terms of RPM, anywhere from 100 to 300 is probably decent for like a car like this. I think these motors spin at 180 RPM, and it's a decent speed. Torque, you probably don't have to worry about the small cart like this. Voltage level will just determine the batteries that you use. Current will determine how you provide the power, and then size just for mounting. So the thing that's tricky about controlling motors is you can't just plug them directly to the Arduino, because motors will most likely require more than 5 volts to run. But you also, even if like these require 6, and you could be like, well, 5 volts, 6 volts, they're very similar. But you also don't want to attach them to your regulated power supply, because the motors, when they're drawing large amounts of current, there's going to cause voltage dips. And your regulated power supply is what comes from the Arduino, and it's very close to 5 volts. The Arduino keeps it at that level. But if you attach a heavy load to that, it might start dipping, and then the Arduino won't function properly, and any sensitive sensors that are connected to that 5 volts won't be receiving the right voltage level. They could get destroyed. So in general, we want to have dirty and clean power. And you guys know this from ohm, and that we had our clean power and our dirty power. But yeah, the clean power is the regulated power that stays at a set voltage level, and it's specifically at the level that our logic works at. And the dirty power, you know, you guys are using a 7.4 volt battery, you guys are using a 6 volt battery. That's not a huge concern when we're working with the motor. So, the other thing is that motors are going to require more current than the Arduino can just supply by itself. What did I say? I think the Arduino can supply 400 milliamps maximum, or no, 40 milliamps, and most motors require at least 200 milliamps. These small ones require, I think, 200 milliamps, but as soon as you start getting a little bit bigger motors or more torque or higher voltage level, it's going to be a lot more. Maybe an amp each on ohm, you know, that's like 25 amps, 30 amps. So this is what I was talking about. When you have your clean and dirty power, the way I like to do it, if you're using a breadboard, just set aside that maybe your top rail is going to be the dirty power, and that's connected to the unregulated voltage supply, and then the bottom rail is connected to the Arduino, which is the clean 5 volts. And it's always important that we have a shared reference point, so that's why we just have one black wire going across the top. So for the Arduino to turn on the motors, we're going to need to supply more current than the Arduino can handle. So basically we'll want a device where the Arduino can provide a little bit of current, and the device will be able to switch a lot of current. So have any of you guys worked with transistors before? You guys heard of transistors before? So normally, like if you guys were in a circuits class, we'd probably they would introduce transistors first and then move to MOSFETs. But because MOSFETs are a lot better, they have a lot of key advantages, I'm just going to jump in and talk about MOSFETs. I actually have, when I did this last year, I talked about transistors, so I can upload that slideshow, but the concept is basically the same, and everything we talk about will basically be not everything, but the same circuits that you build with MOSFETs here, you could also just swap those out for transistors and change a couple of things, but the key idea is the same. But yeah, like I said, we're going to talk about MOSFETs. So with transistor, real quick, a transistor, you supply a small amount of current to a pin. It's a 3-pin device. You supply a small amount of current to one pin, and it switches a larger amount of current between the 2 other pins. MOSFETs are similar, but they're a little bit different in where you supply a voltage to a pin, and then it switches a current. So the advantage to MOSFETs is you don't have to provide as much current. There's less power loss. But this is what the MOSFET looks like. Well, at least like the circuit symbol. There's a semiconductor that acts as a switch or amplifier. We're not going to talk about how they act like an amplifier because that's complicated. You need to know a lot more about how they work. But yeah, the key part is that a small input voltage allows a large current to flow. And that input voltage is going to go to the gate of our MOSFET, and then if that input voltage is present, then a large amount of current is going to be able to flow between the drain and source. There's 2 different types of MOSFETs, a P-channel and an N-channel. So yeah, important characteristics for all MOSFETs. Just when you're talking about MOSFETs, there's this VDSS, which is drain to source breakdown voltage. So this is the max voltage the MOSFET can switch. And then similarly, there's this ID, which is the continuous drain current, the max current the MOSFET can switch. So when you're selecting a MOSFET for switching application, you need to check those 2 characteristics and make sure, can my MOSFET switch the load that I want to drive? So if you have a 5-amp motor that requires 24 volts, you need a MOSFET that can handle both of those characteristics. Then we have this VGS threshold, or sometimes it's just called TH, and that's voltage, gate to source threshold voltage. So this is the minimum voltage difference between the gate and the source required to turn the MOSFET on. And then finally there's this RDS, which is drain to source on resistance, which is basically when we turn on this MOSFET, you can see, I guess I can point over here, the drain to source. This is going to act like a switch, so it's going to be closed, but even switches have a small amount of resistance. And ideally, we want the smaller the better. Because if it's a large resistance, then it's going to result in a drop in voltage, which results in wasted current, wasted power. So when you're selecting a MOSFET, ideally you'd like to select one that's RDS as low as possible. And then with the VGS, this is what turns on the MOSFET. So you want to make sure that this is within the voltage level of whatever logical device will be turning on the MOSFET. So in our example, we're using an Arduino, so we'll want to make sure the VGS threshold is around 5 volts or hopefully less. So with P-channel versus N-channel, I said transistor. It's supposed to be MOSFETs. In general, when you're connecting it, this is what you follow for both MOSFETs, but then there's other things that are different. The drain is always connected to the device you want to turn on. The gate is always connected to the switching source, in this case the Arduino, which is like our input, and the source is always connected to the power supply. For an N-channel, the quote-unquote power supply is actually just the ground. So this is called low-side switching. Basically what the MOSFET is doing is providing a path to ground. So you have the load up here, you can see it's plugged in, but it doesn't have a complete circuit yet. It doesn't have a path to ground. And so what this MOSFET does is when it's turned on, when a positive voltage is applied to the ground, then it can switch a large voltage from drain to source. Yes. So yeah, this is called low side switching, and the way I like to think about it is in channel you can think negative, so the source has to be connected to negative, and then the gate is always going to be opposite of that, so you have to supply a positive voltage to the gate. For the P channel, it's actually the opposite. This is the same. No. Wait, why did I wire up that up wrong? I'm sorry, this picture is wrong. I should have checked this before. With the P channel, your load should be down here. I didn't bring a marker up. I'm sorry. So yeah, but the load is on the other side, on the drain. Like I said, the load always should be on the drain side. The source is connected to positive 5 volts. Or not positive 5 volts, but your positive voltage supply. So with P channel, you can think positive. You connect your source to positive. But the gate is negative, so to turn this on, you need to send a low signal. Which, yeah, we'll show that in a minute. Yeah, I'm sorry this picture is wrong. But just imagine that this load up here is actually down here. The source is connected directly to the positive voltage. And so this is high side switching. We're providing the component with the voltage level that it needs, and it's always connected to ground. And then we need to send a low signal to the gate to turn it on. If we send a high signal, we'll actually turn it off. So the key advantages of MOSFETs, MOSFETs can generally handle more current and voltage than transistors. MOSFETs require a voltage to turn on, while transistors require a current. Because current's a flow of electrons, that is kind of just a wasted power. If you're just providing a voltage level to the MOSFET, it doesn't require as much current to flow, so they're more power efficient. And because they're more power efficient, you can pack more MOSFETs onto a board. You can pack them tighter together. So that's why I think in the logic chip industry, they have switched to MOSFETs, so they can pack a lot more together, tighter on one chip, and save money and save space. Finally, MOSFETs react better than transistors when the load must be switched at high frequencies. So if you're turning a load on and off very quickly, a MOSFET has some characteristics that makes it better for that. So all in all, these are reasons why we're going to just talk about MOSFETs and not worry about transistors today. So what we're going to do is this is what we're going to build right now. Yeah. So this is, does anyone remember with the MOSFET down there what switching that is?
What's this? P.
This is an N-channel MOSFET because the source is connected to negative, and this is low side switching because our component's already connected to the correct voltage level up here. So it's low side switching because we're providing the low side the path to ground. So this is how we connect up an N-channel MOSFET. Some of the other components, why they're here, this RGS is a pull down resistor. So by default, if our input is not on, we want the gate connected to ground so that the MOSFET's turned off. So in case the Arduino, we don't want when the Arduino is off it to be kind of ambiguous right here at what voltage level it is. So just like with a button, we have, in this instance, we have a pull down resistor because 0 volts turns the MOSFET off. And then this RN is a current limiting resistor, just so when you first power on the MOSFET, there is going to be a flow in current to turn it on quickly. And then once that flow of current has been established and it raised to the correct voltage level, then there's less current flow. But Arduino can only supply, 400 or 200 milliamps of current. So we don't want to exceed that. So that's what this resistor is. And so I calculate here what those values should be. If we say we only want the Arduino to supply a max of 200 milliamps, then we just use our formula V equals IR. We know the voltage, we know the current, so we're going to separate the resistance over here by itself. Then we're going to plug in 5 volts and our 0.02 and calculate a resistance of 250. And so I think in a kit we have 220 resistors and we have 330. So either one of those will work fine. And then VGS just serves as the pull down resistor. So as I mentioned before, a good value is 10 kiloohms. We also, the reason to have it be a very high resistance is because this kind of turns into a voltage drop. Some of the voltage is going to be dropped by this resistor, and the rest is going to be dropped by the pull down resistor. And so if this value is very high, less voltage is going to be dropped across this Rn, and so the voltage at the gate is still going to be about 5 volts, maybe it'll be 4.8 or something like that. So a high value like 10 kiloohms works well. And yeah, I guess I calculate up here. If we use 10 kiloohms and 330, the voltage out is 4.84, which is very close to 5 and still high enough to turn on the MOSFET. And then the final component, this is this flyback diode. Because motors can be treated as an inductive load, when they stop, there's a sudden shift, this reverse voltage. The way you can think about it is like, you guys know from physics, the current supplied to the motor spins the motor, but if you just spin the motor, then you suddenly provide the current. It turns into a generator. So when the motor turns off, it still has some inertia, it's still going to spin and wind down, and that creates a backwards voltage that can fly back into your electronic system and destroy it. So we don't want that to happen, so we want to provide a path for that reverse flow of current to flow, and so we use our diode. So you guys, I know you guys should know. Do you remember what the diode does? Yeah. So the way it's hooked up right here, when we're providing our voltage source right here, current can't flow this way. It's pretty easy to see because the diode has that line there and an arrow. Current can only flow this way. But under normal circumstances, this is going to be a high voltage. This is going to be close to ground when this is switched down. So current's going to want to flow this way. It's not going to want to flow back to the higher voltage. It wants to take the path of least resistance. But when the motor is suddenly stopped, but there's still this inertia value, it's still rotating, it suddenly switches, and this becomes more positive than this side. So then we have this reverse current flowing through the diode, instead of trying to flow through here and maybe destroy some of these components.
So just to clarify, I guess.
Sure.
Understood. So is that because the north side of the motor in that drawing would be more negative than ground?
It wouldn't be more.
It wouldn't head to ground in that scenario.
It wouldn't be more negative than ground, but this is going to be a path of least resistance than flowing through these switching components.
Okay.
This is almost like a direct short to ground, and this is would have a little bit of resistance.
Okay.
Yeah. So you guys are going to wire this up. I'm going to give you all the components. This is outside of what the kit has. So we all got this working, sort of ish, not really. But important part is this allows us, using the MOSFET, we can switch a higher load than the Arduino can normally handle, both in terms of voltage and in current. So this example, it's a motor, but you could have a light bulb, you could have a really big, I don't know, some other load that can't just be turned on by the Arduino. So we talked about there's two different kinds of MOSFETs. There's N-channel, which we just used, and there's P-channel. And the P-channel was with the high side switching and use a negative signal to turn it on or off. And so this is how you might think, okay, if you look back, this was the N-channel, we did low side switching, the source is connected to ground, the drain is connected to the motor. What if we just do that for the P-channel, but because it's P, the source is connected to positive, or the load voltage, our gate's connected to the Arduino, and then our load's connected to the drain, and the other side of the load's connected to ground. And you might think that this would be a way to wire it up, but this actually wouldn't work because the gate has to be to turn the P channel on. The gate, there needs to be a voltage difference between the gate and the source. The source is connected to the positive source. Here it says 5 volts, and I'll explain why that in a second. But let's just pretend this said the 6 volts or the 7 volts that we're using on our system. So this is 7 volts. So to have a negative voltage on the ground in reference to the source, the ground just has to be less than the source voltage. So a voltage of 0 volts, that would mean there's a negative 7 voltage difference between gate and source. So if we send a 0 signal on the Arduino, it would turn the MOSFET on. Now if we tried to turn the MOSFET off though, and we sent a 5 volt signal on the Arduino, we have a 5 volt signal on the gate, and we have a 7 volt source. So there's still a negative 2 volt difference between the source and the gate. So to actually bring the gate to a neutral where it's not a negative voltage difference, you need to supply the same voltage that the source has. But the whole point of the MOSFET is that you're switching a very high load with a higher voltage. So you can't just connect an Arduino directly to the P-channel MOSFET the same way we did with the N-channel MOSFET. And I talk about that here. What was the other point? Oh, and then here we use a pull-up resistor. Okay, so by default, say this is 7 volts again. By default, this is going to be connected to 7 volts. So great, it's going to be off. The problem with that, though, is now the Arduino is connected to that gate. So the Arduino is connected to that 7 volts, and we don't want to connect the Arduino to something that's not 5 volts, that's higher than 5 volts. So there's no real good way to connect directly to a P-channel MOSFET to a motor. So if you were just going to switch the motor on and off, this would be a fine way to do it with the in channel at the bottom, or you could use an in-channel MOSFET to turn on a P-channel MOSFET to actually turn on your motor. I couldn't find a picture of a motor actually being turned on, so just pretend that this is a motor for right now. But this is our P-channel MOSFET. But basically what we want is, by default, there's a pull-up resistor, so by default it's connected to the same source voltage. So the difference between the gate and the source is 0 volts, which means that it's off. But if this was connected to ground, then there'd be a voltage drop across here. The gate would be connected to 0 volts. Then there'd be a negative, in our case, a negative 7 volt difference between the gate and source, so the P-channel MOSFET would turn on. And then once again, because this is 7 volts and this is going to be a lot higher voltage than what our Arduino wants to handle, we use this in-channel MOSFET kind of as a buffer between the actual Arduino and the higher load. So yes, if you wanted to turn on a P-channel MOSFET, you would have to use an in-channel MOSFET. This in-channel, like I said before, transistors and MOSFETs can kind of be used alternatively. So you could replace this with a transistor. Now, with what we just did, we turned the motor spun in one direction. And as Will found out, if you switch the leads of the motor, current flows the opposite direction and the motor spins the other direction. So ideally, in a lot of robotics applications, you'll want the motor to be able to spin in forward and reverse. Like with the diff drive vehicle, which is the most common, you spin the motors forward, you can turn in place by spinning one backwards and one forward. So you need to have a way to pass current through the motor in both directions and be able to switch that. And you might think that that requires more switches, and it does. It actually requires 4 different switching devices. And so this is the H-bridge setup, because it looks like an H. And there's 4 different switches. If A1 and A2 are switched, then there's a path from the voltage supply through the motor in this direction, then to ground. if you turned both of these off and then turn the others two on, current can flow the opposite way. And so now we have a way that by controlling these 4 different switches, we can spin the motor left or right, or clockwise or counterclockwise. And so, as you may expect, we can swap out all of those switches and replace those, instead of physical switches, replace them with MOSFETs. And so that's what we have here. All these MOSFETs have a flyback diode for protection, and all the MOSFETs still have either the pull up or the pull down resistor and the current limiting resistor. The suppression capacitor wouldn't be necessary in a hobby circuit. I'm not even quite for sure what that's for, so just ignore that for a second. But yeah, does this make sense? How you can have all these switches. Does anyone see a potential problem with this? Well, if we wanted to control this with the Arduino, what problem might we face with controlling all these switches? Because like what we did is we controlled, these are in channel, because you have low side switching down here and you have high side switching down here. So these MOSFETs have to be in channel and these have to be P channel. But the problem is we can't control P channel directly. There's also a problem which is called shoot through. But basically, if you ever turned A and B on at the same time on the same side, there would be a path directly from your supply voltage to ground. So voltage would flow through this MOSFET, but then it wouldn't flow through the motor, the load. It would go directly through this MOSFET, and so now you have a very low resistance path directly to ground. And remember, this voltage is often 7 volts or 24 volts, so that's bad. Your MOSFETs would be blown. Maybe if you're lucky, your Arduino won't be blown, but it probably would. It'd be very bad. That's what this issue is. And then, yeah, like I said before, you can't turn the P channels on. There's also an issue. You have to get into the weeds a little bit more about how the MOSFET works, but because we're limiting the current flowing into the MOSFET, you limit, or it slows down how quickly it turns on. So if you were going to switch this on and off rapidly using PWM, which would be how you could like adjust the speed, you would have a limit of how fast you could switch this on and off. This is less important than the other two issues, but that is a potential concern. So ideally, we'd want to actually send a little bit more current than the Arduino can supply to the gate of the MOSFET when it first turns on, so that it can turn on completely a lot quicker, and then we could switch it on and off very quickly. So to achieve all of this, we can isolate the Arduino from the MOSFET H-bridge through these, I can't think of the name, the photocouplers. And what the photocoupler is this is a transistor. You could think of this as a MOSFET for a second. This is a MOSFET that can switch a load, but instead of having a gate pin, it actually has a sensor that senses how much light is there. And so this is a transistor, so this is a phototransistor, and you could use that in a circuit, like how we use a photoresistor. If there's a lot of light, or if there's a lot of light, maybe it turns on. If there's no light, it turns off. It could be a switch like that. But in this example, we use it to isolate our Arduino from this circuit through this light signal. So if the Arduino inputs a signal on this H pin right here, this LED turns on, this turns on this transistor, and so now we've passed information, but the Arduino is completely isolated from all of this. And so now this transistor is able to supply more current to each of these MOSFETs than the Arduino can, so we can switch it faster. Also, because this can turn on the P-channel MOSFETs up here, because it can now connect, it can switch this 12 volts because it's a transistor, it can switch a higher load. And then finally, we actually have connected both of these MOSFETs together, so these can never be the same state at the same time. if we think about it, and if this transistor is off, we have this pull-up resistor to our supply voltage. We'll say 12 volts in this example. So there's 12 volts here, which turns this on, and there's 12 volts here, which turns this off. And the same thing over here. There'd be 12 volts here turning this on, because these two are P channels, and these two are N channels, so these two are off. So these two being on at the same time is fine. There's still no path to ground. But then as soon as we turn one of these on, there's now a path, or one of the photocouplers on, there's now a path to ground. So because this turns to 0, wait, no, I said this wrong. I'm sorry. With the pull-up resistors, both of the N-channel MOSFETs are on, and both of the P-channel MOSFETs are off. As soon as you turn a photocoupler on, one of the N-channels will turn on, or one of the P-channels up here will turn on, and this one will turn off. And now you can have current flow through the motor. I'm sorry, I said that wrong. Does that make sense, though? Confused everyone slightly, including myself. But in the default state, both of these N-channel MOSFETs on the bottom are on, so there's no path from 12 volts to ground. But if you turn this on, this photocoupler over here, you allow there to be a path to ground, so this is going to read 0 volts. 0 volts isn't enough to turn on the N channel, so this is going to be off. 0 volts is what we need to turn on the P channel, though, so this will turn on. Now we can have a flow of current through this P channel and through this N channel, which is default on to ground. And even if we turned both of these photocouplers on at the same time, that's fine. Now we've just turned on both of these P channel MOSFETs, so now there's still no path to ground, and so there's no shoot through or anything bad like that. So ideally, we take the time and make one of these, and maybe if we have time, we could do that next week. We're not going to talk about that. Finally, you might be thinking, this is starting to turn into a lot of components. This is going to take up a lot of space on my board. Is there an easier way to do this? And there is, and it's actually included in the kit. There's this L293D motor driver IC, or IC stands for integrated circuit, so it's on a little chip. I'm sure you guys can find it in the kit, but yeah, it looks like this. What is it? A 16-pin device, and it basically contains 2 of these H bridges inside and all these small little transistors, and you can connect 2 motors to it and then turn them on and off from your Arduino. So this is very popular among hobby robotics because a lot of times you have, like I said, a diff drive robot with 2 motors that you need to spin the motors forward and backwards. So you can use this chip to turn them on or off with the Arduino. Now, the biggest limitation of this chip, and that's why I spend all the time talking about MOSFETs, is its current output. Its max continuous current is 600 milliamps, which for these motors is fine, but as soon as you start getting into bigger motors to handle either a higher load or things like that, you're going to take a lot more than 600 milliamps. You could take 1 or 2 amps, and so this chip would not be able to do that. But probably for any hobby project you guys might want to do at home, this chip would be fine. So yeah, so those are your different options for controlling motors. And then once again, maybe in your application you just need to spin the motor one way. There's no reason to implement a full H bridge. You can just use one MOSFET to turn it on or off, and that saves a lot of time. So yeah, no, that was a lot of stuff at the very end, but you guys have any questions about that? If you ever wanted to wire up this chip, the one that's on the kit, it's fairly self-explanatory. The biggest thing you need to watch out for is, I think this VS on pin 8 is your supply voltage to the motors, and this VSS is your 5-volt logic supply. And then you've got these 2 enable pins, which enable the motor. So if they're always connected to 5 volts, then it's always enabled. Or you could have the Arduino disable the motor if you wanted to. And then you've got inputs and outputs. And these inputs basically are just like each of these inputs that go to one side of an H bridge. And the outputs are right here that go to the motor. Yeah. And so maybe even next time we could wire up this one, because this one doesn't take too much time. It's only one component.